All right, then welcome to my quick presentation about my small artificial life project. I was very fascinated by the ant colony behavior and by the interaction between the ants and basically the emergence of this path. And so I wanted to do something related to this. And for me, the question was if I can make it that the ants are actually learning how to use or how to place pheromones and then also use those pheromones. So basically, in order to simplify the model, I guess, I'm assuming that these ants live in a two-dimensional world, which is just a grid. And then right here, the dark red would be the home position, the light green would be the food position, and the ant would be, for example, here in the center, and it has a certain vision range, so it can see within a certain radius. And then there's some pheromones that it leaves, and in the original idea, like when doing the normal simulations, you first leave the two home pheromones, and then once the ant was at a food source and it tries to return, it leaves the two food pheromones. And so these are also placed in this world. And then the idea is that the ant would get all of this information, I would flatten it, it would go through some hidden layers or some fully connected neural network, and then first decide one of four actions, for example, which direction to move. And then also the basic or the initial idea was to have it also learn, okay, which pheromone do I actually want to leave? And then using all of this, then I update the position, then I start again at the beginning. So initially I just implemented this and tried to have it learn, and basically nothing worked. So I was trying to figure out why did nothing work. And the first thing in order to see, okay, does my system actually work, was, okay, let's reproduce the classical ant simulation where I hard code the dynamics. And so this is basically what the ant sees. And I'm basically splitting it into two different parts. First, if it can see the food or home, specifically like what it's interested in. So if it's interested in finding the food and it sees the food, then it's just calculating the direction to the food source, calculating the dot product with all the possible actions it could take. And then this gets a score, and then I use the softmax on the score to get the probability for all the different directions to add also some randomness factor. Yes, where it gets a bit more interesting is if there's no food source available. It's a bit weird with the beamer. And what I'm doing here, in order to test different vision ranges and always be able to just use this simple rule, I guess, I'm applying a kernel to just basically apply that or look at all the pheromones in the top left corner that I'm interested in, top center, top right, and then so I can kind of rescale a completely random sized input into just this 3x3 field. And then again, the probability for each score is just the probability to take a certain action is the score that I'm associating and then just normalized. So in this specific example, for example, the assumption would be, okay, here, there's the pheromones go the highest. And so it would try and take a step in this direction. And now, how do I simulate the world? Also pretty straightforward. So one world step consists of, I select the first ant, I do food management. So if the ant is currently sitting on top of a food, it picks up the food source. If it's having a food source and it wants to go home, it's dropping the food source. It looks at its environments, it forms some step, it leaves some pheromone trace. I go to the next ant, I do the same. And then after I've went through all the ants, I'm clipping all the pheromones to not have exploding values. And I'm diffusing the pheromones, and then I'm also letting them slightly evaporate. And then I do the same again. Now, interestingly, my assumption was, okay, now everything is fine, everything works. I implemented all the rules that I've known from the videos or other simulations. However, for some reason, stuff still wasn't working, which is very trivial if you think about it, why it wasn't working, because the problem is the strength of the pheromone that's being left behind needs to depend on how long ago have I been picking up a food source or how long ago have I been dropping a food in order for a gradient to emerge, I guess, and then following the gradient to the specific thing, which, yes, I know, it's very trivial and clear, but it wasn't stated anywhere specifically, and it took me a lot of time to figure this out. So if any of you are ever trying to do an N simulation, for me at least, this was very necessary. Otherwise, stuff didn't work, and I was super confused why it didn't work. Anyways, now, having implemented all of this, I was able to actually get it working. So right here, we can see the blue is indicating an ant that is looking for food. This is the position of the food. It's not the best simulation. I'm sorry for. I hope it's kind of visible in a second. And I marked the home position with the blue circle and the food position with the red circle. And initially, they're all looking for food. So the green is the true home pheromone that they're leaving, and they're just randomly trying to find the food. And as soon as one ant finds a food source, it changes color to red. And then we can see it's leaving the blue pheromones, which are the two food pheromones. And then we can see that the system creates the behavior that we want. Everything is happy. I'm fine. Finally, something works. Success.
So these ants have the brain, the correct brain.
They have the hard-coded brain, yes. They have the hard-coded brain, and yes. Okay, quick recap or quick observations from finding this in the first place. So what I've been observing is that this strongly depends on the specific parameters that I've been using. And if I'm changing the food source or the final distance that they need to do, I need to basically change my number of ants, how strong the pheromones are that they're leaving, all these kinds of things. And specifically the most important one was how fast the pheromone that the ant is leaving behind decays. So within the ant, how much basically the time that it hasn't interacted with either home or food, how much the influence of this is. And right here, for example, I've tweaked this. And again, it starts the same. In this simulation, it decays much slower. So it's still looking kind of good, I guess. It's also going to find some food, and then it's going back. But then it's building this weird cluster. And then everything is just going there. And basically, the system gets trapped in the state. It's not going out. Yeah. And so my observation was that it's very strongly depending on the specific decay rates, which might also be interesting if anyone tries to replicate something. Yes. Okay, now my original idea was to try and have the ants learn their behavior. And spoiler, sadly, I didn't manage to get it to work, which might be strongly influenced by me not having the most knowledge in neural networks and how to train system. However, I'm going to present the approaches that I've been using in order to try and get something to work. So the idea is, or the problem is that the ants are supposed to learn the pheromones, but for this, to train them on this, they need to have a world where the pheromones are in it, and how they leave the pheromones depends on them themselves. So my initial idea was to say, okay, I'm just initializing my ant net, I'm letting it randomly play, and then I'm using each individual time step of each ant. I'm taking this as a training data point, and then I'm also labeling it with the correct direction it should take, because me as an outside observer knows where's the food source, where's the ant, so which direction should it technically go. And then I'm running this for a certain amount of steps. I'm storing all these best moves and storing all the data. And then based on this, I train my set. Then I redo this for a couple of iterations. Then I'm increasing my system size to basically have my system become harder and harder to push my system towards getting better. Sadly, this didn't work. They didn't really figure out how to do anything. And then the other approach, or the second idea was, okay, maybe it's very hard for them to find a proper gradient. So let's use genetic mutation, where again, I'm also setting up my parameter with a simpler example in the beginning. And instead of just one world, I'm setting up 100 different worlds. I'm letting them all run. I'm assigning a score to how many food sources they've picked up, dropped, and how many steps they've been making in the correct direction. I'm calculating the score for all of my 100 simulations, and then I just keep the best ones of these, slightly mutate them, reiterate, and then also increase the world size. And sadly, this also didn't work for me, at least. The problem for both of these is that running those, for me, took a very long time. And as said before, it's strongly dependent on the specific decay rates. So it might be that I've just not been able to find the correct decay rates in order to have my system be able to learn what is going on. And with this, we get to the key results that I've been able to find. So the first is that it is possible to do an ant simulation in a discrete world. All the videos that I've seen at least always had a continuous world where the ant had a specific velocity and then they were changing the angle in which it was going, which actually might make the simulations more resistant because then you don't, or it's harder to get this clumping, flocking behavior. So I'm assuming that this momentum term helps for stability. However, I was not able to, or I tried to put this momentum term also into my simulations. But then the problem is that based on this grid structure, I'm basically creating a star because it's more likely to go up, down, left, right, and then going the direction, so it's not continuous, and then stuff doesn't really work. Maybe someone has a nice idea on how to fix this also in the setting that I'm proposing. Yes. Then the third one, there's a very, very strong influence of the specific parameter configuration. And finally, sadly, I was not able to learn the behavior. If anyone, I also tried doing reinforcement learning, but I have no background in this at all. I just followed some tutorial, and so it's very high likely that I just messed something up. I still find this very interesting. So if anyone has more background in this and is also interested in this, I would love to try and figure out how to make it work. Yes. And with this, I conclude my presentation. I would love to discuss any questions that might have emerged and ideas how to tackle the problem. Yes.
How do you parameterize the grain of the ant, and what is its input?
So the input of the ant in here is basically, so these are 4 different channels, 1 channel for the food, 1 channel for the home location, and then 2 channels for the 2 different pheromones that I'm proposing. And then I'm taking all of these informations and I'm giving it the food as the first spot, and then I'm just flattening everything else and feeding this into my network, which also might, like there might be smarter ways to do this. I also tried with applying this kernel that I'm using here, also first applying this to reduce the parameter space. But both approaches didn't work. But in the reducing the parameter space, I fixed this kernel and I didn't let it learn. Maybe having this kernel be learned could also improve something.
And what is the output of the brain?
The output of the brain is first one vector which corresponds to the values for the directions, which I apply the softmax on.
It's probabilities to move in that.
This is the probabilities, yes, and then it's selecting one of the probabilities based on the a softmax, like I feed it into softmax, and then and then the other I just cut at 0, so I apply ReLU, and then the pheromones I don't do anything else on.
So ants lie in the grid, or
ants do not see each other, if that's the question. Ants only see the pheromones that other ants are leaving, but they don't see other ants.
But they move in the grid.
They move in the grid, yes.
What happens if they collide?
They can collide. There's nothing.
Then there's only one ant left.
The ant position is not stored in the grid, but the ant position is stored extra in the ant object, and so initially I also had the ants in there, but then because I didn't want them to disappear, I had exploding values, and I didn't know how to keep the number of ants and also preserve that values are not exploding.
Yeah, it's an agent-based model, but on a discrete grid. It's not really a CA.
I did a lot of experiments on similar things. I was using grid free, so ants have floating point positions.
Yeah.
And I tried some similar stuff to you.
Okay.
So, like you said, if someone is interested, we can talk.
Nice, that would be very nice.
Sure. Other questions?
Yes.
So I don't have ideas on how to make it work better, but I just wanted to understand more what happens when you have this problem of like they all come together.
Yes.
Like you said, you have one more time for the pheromones.
So we're talking about this. So basically what's happening is that the pheromone, or that a lot of ants are collapsing at the same time, and so their values are adding on top of each other, and then the gradient is kind of inverted, like the gradient doesn't lead home anymore, or it doesn't lead to food anymore, but there's a lot of ants here, so the two food or the two home gradient basically, because they're mostly blue, the value is highest here.
They can't escape like they are.
They can't escape anymore because each ant wants or thinks that the true home location is here, but because there's also a couple of ants that have food in here, they also think that the true food location is here. And so both are being stuck there. There's very few red dots in here that are keeping the blue ones trapped, and the majority of blue dots keep the red dots trapped.
So okay, so the ants can see the food in the place, but also in the other ants' arms.
The ants don't see each other, but they see the trace that the ants are leaving. And the ants that are trying to get home leave a true food trace, and the ants that are trying to find food see this true food trace. And because the majority of ants is here, the highest value of this true food is also here. And the true food, or the ant that is trying to get home, also sees that the true home is highest here. And so they're both getting stuck here. Does this make sense?
Yeah.
Okay.
By the way, this also exists in real life. So it's called a death spiral of ants.
Okay.
So it does happen that ants just get stuck in kind of a loop of pheromones, and they just march along the thing in a circle. You can Google it, and you have videos on YouTube, and they just die. And they do exactly that. Precisely. So it's not entirely.
Okay. You also.
That was my thought.
Okay.
Nice. Okay, I didn't know that, so
Yeah.
I guess that's nice.
Other questions? Otherwise, I had a question. So you mentioned, this important property that kind of the strength of the pheromone that you leave depends on how far you are from
Yes.
where you come from,
Yes.
either home or.
Yes.
I think, that's indeed something that I hadn't thought about. So I think one way to mitigate this is if you allow the ant only to look in front of it.
I tried this as well.
The problem is the discretization makes it kind of.
Because of this, I was extending it that it can go through all the surrounding parts. And then I was saying that it can, if it's going up, it can go to up left, up straight, and up right in the next step. If it was going up right, then it can go up right, and right.
Yes.
So I was limiting it this behavior, it didn't fix it.
Okay. Indeed, I wonder because if you have just the front cone of seeing, in principle, this prevents you from doing a loop, right? You just follow the pheromone and you cannot do a very kind of short loop. So this solves it. But still, I don't know when kind of they find food. How do they know when you have kind of the two-home highway? How do they know which direction you should take the two-home highway? This is a And so you're doing with the gradient of kind of the pheromones.
I'm
I don't know in other simulations how they do it.
So the video that you referred, they don't say it specifically, but if you look at the strength of the dots that they're leaving,
you see that
they're decreasing.
Okay, I see.
And so I'm assuming that they're also doing it,
probably,
but not saying anything about it. And I tried figuring out the code, but I was stuck in a maze of.
And so just to make sure, so the decrease in strength of the pheromone that you leave, this depends only on the number of steps you took from your last
just having
action.
an exponential. So the moment I'm picking up food, then I'm resetting the value. And the moment I'm dropping the food, I'm resetting the value, and then I just have an exponential that every time I'm multiplying some rate.
But the same thing from home or not?
For both, for home and for food.
So in this case, why don't they kind of stop producing pheromone at some point and break away?
The strength of the pheromone they produce gets lower.
It doesn't go to zero.
I mean, it's exponential decay, so it gets slower, but it's never zero.
Okay.
But the problem is that so I would assume that if I let the other pheromones stay longer, like the pheromones that I've already replaced stay longer, that then it might happen less, because then the true home direction would be stronger, and what they are adding new would be comparably lower.
That's interesting. I didn't think of that.
Yeah, me neither, and I was very frustrated that it didn't work.
It's good that it always works.
Yes.
Any last questions? Okay. All right. Thank you very much. We could have played twice. I didn't think about it.